So quantum computing, it's a field I've been observing for the last 5 years, and it's got great promise to benefit science, technology, and therefore society. And like any technology, it's a double-edged sword, able to affect civilization negative as well as a positive manner. And a significant negative is the theoretical ability to break major schemes of current deployed encryption, including elliptic curve key exchange. So before looking at that and the implications of blockchains, I'm going to give an overview of the state of the science so you guys can see really where this is and what is the likelihood of the time scale for the realization. And I'll move on to So it's a high level of QC intended to give a feel for how it works, where the technology is at, what's being done in post-quantum cryptography, and how long it will be before real-world effects from QC are experienced, especially the effect on elliptic curve cryptography. And then finally the talk concludes with a proposal for Nexa to leverage this emerging technology as a benefit instead of being blindsided by it. So getting ahead of the QC growth curve may add significant potential value to a cryptocurrency by delivering on the promise of maximum security for user funds. So we're all familiar with the classical bits, as digital computing has been a fundamental driver for living standards for 50 years. So there's two other paradigms of bit-based computing which will rise to complement classical computing. So probabilistic computing with oscillating natural systems is very new, and the experimental proof of concept is only in the last 2 years. Now, classical computing is here to stay, as it's much more versatile for control, I/O, UX, UI, sequential problems, etc. So we're going into a hybrid future. So the unit of storage for information is a quantum bit, or a qubit for short. So superposition enables quantum algorithms to utilize other quantum mechanical phenomena, interference and entanglement. So together, superposition, interference and entanglement creates computing power that can solve problems exponentially faster than classical computers. So any uncontrolled measurement of a qubit will collapse its state to a defined value. And qubits are described mathematically as a region of Hilbert space, which is demonstrated by the block sphere there. It's possible to update non-data information in a qubit without collapsing its state, which is fundamental to error correction. So qubits are just the start, although out of scope for the remainder of this talk. Mention must be made of the potential power of quantum computing beyond binary representation. In multi-valued quantum systems, qubits can be encoded with 3 or more orthogonal quantum states. So qubits the Q-trits are analogous to trits in classical computing, and Q-dits are base 4 or higher. As a consequence, Q-dits offer a much larger state space to store and process information, and a reduction of QC circuitry complexity, and it vastly improves algorithm efficiency. And illustrated is a recent experiment just published last week at the US Department of Energy's Oak Ridge National Laboratory. They demonstrated a fully entangled pair of 8 level Q-dits, which formed a 64D quantum space. In theory, coloured photons can encode 10 or even 20 level qubits. So we could have base 10 computing. Right, so entanglement and gates. Entanglement of qubits is fundamental to general purpose quantum computing. In the classical world, the whole is exactly the sum of its parts. In the quantum world, the whole is greater than the sum of the parts. Quantum entanglement is mathematically described as a linear combination of tensor products in Hilbert space. And qubit states can interfere with each other because each state is described by a probability amplitude, just like the amplitudes of waves. And entangled qubits can be manipulated in a series of circuit gates. So there are varied quantum circuit gates which operate on a combination of qubits to support computational processes. So 3 principal ones are the Hadamard, which sets single qubit states, C0 for entangling and disentangling qubits, and Toffoli, Italian word, Toffoli gates, controlled not gate with 3 inputs and 3 outputs. So reversible gates are an essential requirement for quantum computing because waste heat will cause decoherence of your qubits. So error correction is becoming a very important part in quantum computing prototypes. Decoherence occurs when qubits interact with anything external in the environment. Hence, a major part of the QC development is removing unwanted sources of radiation and heat, extending coherence duration and correcting qubit errors caused by premature decoherence of part of a QC system. So quantum error correction is a set of techniques to protect quantum states from the effects of decoherence. In less than 25 years, it's advanced from a situation where many prominent QC theorists doubted that QEC was even possible, to a large field with well-developed theory, thousands of papers and international conferences. So without error correction, quantum computing would be restricted to toy problems. The first prototype applications of error correction occurred in 2014, was significantly advanced. So it's possible to deduce which error occurred in a qubit by performing a suitable stabilizer measurement without acquiring any information about the computational state that was stored in the qubit. So corrections are implemented by using an algorithm to update orthogonal subsets of state data in Hilbert space. So how can we possibly update Hilbert space? The answer is using extra qubits in the QC, which are green in this diagram. So some researchers are very bullish and consider that in theory, quantum computations of any size can be done without major improvements of technology, but that's not really the case. The number of correcting qubits grows exponentially, such that 1,000 qubit QC may just provide 5 clean logical qubits for computation. So there's a couple of enabling technologies here. The first one's quantum simulation. So they're a valuable tool to prove QC circuit design. The state vector is the first choice of simulator for QC research, able to maintain a complete numerical description of an evolving qubit state. So perfect simulation is very resource hungry. To simulate 40 qubits at double precision requires 16,000 gigabytes of memory. And this was actually done using the AWS network. So the computer shown below is Fugari or something. It was, until recently, the world's most powerful supercomputer in Japan. But I don't think even that's enough for 40 qubits. The AWS was able to do it though. And tensor networks can simulate more qubits, but it does have other drawbacks. So a leading example uses 900 GPUs to simulate 1680 qubits, and it was able to solve a graph with 3300 vertices, which I'm sure Peter would appreciate that one. Okay, so quantum annealing, and interestingly, that's just down the road from you. I don't know, have you met the guys there? Or?
Well, one of them I went to school with.
Right, wow, okay. So quantum annealing uses entangled qubits to perform iterative searches for lower energy states, and a surprising number of real-world manufacturing problems, optimization or sampling problems, and they're amenable to quantum annealing for solution finding. Recent example is BMW using quantum computing to optimize the location of sensors. And there's a YouTube video about this where it's just a huge improvement over any classical solution. So D-Wave was founded and spun off at the University of British Columbia, and the customers include Lockheed Martin, Google, NASA, Los Alamos. That the annealing computers are finding more applications every day in machine learning, etc., and material science, but they don't use gates. So they're not general purpose quantum computers. So in order to crack blockchain cryptography, we need a general purpose quantum computer. So What's interesting is that there's a whole landscape of these, and I'm just going to cover briefly each one so you can get a feel for where the technology is again. So the R&D prototype and vendor landscape for QC appears very confusing. So in the main it's because there are many different platforms, substrates to use for qubits in a state of superposition and entanglement. Unlike nuclear fusion reactors, where there's only a single viable approach, magnetic confinement, QC can be built in many different ways. And even the list of platforms varies from source to source. So I've selected 9 which are arguably qualitatively different from each other, and it's worth spending a moment on each to get a feel for the sheer variety of prototypes under development and their corresponding different times to commercial realization. So billions of dollars are being spent in this field, and there's 450 universities, research labs and companies working to make QC a viable commercial reality. So the first one, which is quite famous, is the superconducting circuit and the chandelier architecture, which is familiar in the media. So the dilution refrigerators progressively cool the structure, so the top is 4 degrees Kelvin, liquid helium, cooling as it descends until the qubit chip at the bottom is 10,000th of a degree above absolute zero, colder than anywhere else in the universe. The illustration is the exposed insides, which are normally sealed against the environment, and the qubits are controlled by radio frequencies. So in April 2020, IBM had 54 different quantum computers available on the internet and the cloud. And that's what's happening with this architecture, is that quantum computers are being made available in the cloud, and just anyone who, students, researchers, anyone can buy time and just experiment with quantum programs. So the 1021 qubit Condor chip is planned for 2023 by IBM. So another solution is trapped ion, which uses similar refrigeration to superconducting circuits. So the trapped ions are confined and suspended in free space using electromagnetic fields in a magneto-optical trap, or MOT. So the qubits are stored in the stable electronic states of each ion and controlled by the lasers. So the coherence times are up to 10 minutes, substantially more than the usual milliseconds of most qubits, and 1,000 qubit machines are planned by both IonQ and Honeywell. Another technology is photons as qubits. And this one operates at room temperature, as photons make very robust qubits. And California-based PsiQuantum is very aggressive with its roadmap, seeing a clear path to 1 million qubits. And the London-based Orca Computing, with links to Oxford and Cambridge universities, also believes photonic QC will outpace the other platforms. Fourth is cold atoms. So Cold Quanta has been developing QC for 15 years. Their system works by trapping cesium atoms in a 2D array by laser light in an ultra-high vacuum glass cell. By trapping the atoms with lasers, Cold Quanta is able to cool them to less than 5 microkelvin, very near absolute zero. An experiment at the International Space Station achieved the extraordinary picokelvin temperatures. Laser and microwave pulses create the computing gates. And the fifth technology is using the spin of atomic nuclei. Excellent control fidelity, and strontium atoms are preferred in atom computing's QC prototypes, and this particular manufacturer was the fastest to go from a startup to a 100 qubit machine. A sixth one is electron spin. So there's many substrates that offer electron spin, but one that's worth mentioning is doping silicon with phosphorus. And what it does is it allows 2 qubits to form in the one place, one on the nuclear spin and one on the electron spin, and they can be addressed independently and together they're more robust than an individual qubit. And another technology is the virtual positron. So in semiconductors, there are holes which are gaps in the electrons, and they can be excited, and they will behave according to quantum field theory as a virtual particle, a positron, and the positron can have quantum mechanical properties for qubits as well. And a couple of universities, QTech and TU Delft, have created two-dimensional arrays of whole qubits. And another possibility is the colour vacancy centres in crystal. So this uses an electron triplet that occurs with a nitrogen atom impurity in diamond. The electrons are in an excited state known as a colour vacancy. Natural diamonds with nitrogen impurities are not the most suitable because carbon-13 impurities are a source of decoherence for the qubits, which illustrates how fragile superposition entanglement is. So artificial carbon-12 diamonds are best for this technology. And Archer is an Australian company based in Sydney, and they're actually manufacturing nano diamonds and silicon using this technology. And then finally is topological QC. So unlike ordinary qubits, information is encoded in the world line of a quasi-particle, in this case an anion, as it moves through time, which is here the vertical axis in the centre picture. So Microsoft QStation was founded in 2005 and has been working diligently to realise a commercial QC. However, its focus on topological computing makes for a very difficult road, and the scientists have been experimenting with electrons for 200 years. But anions have only been technically usable for a couple of years, and no prototype exists of this technology. So this may be another Microsoft HD DVD moment, and the risk is apparent to them where other QC platforms grab market share and dominate the field thereafterwards. So the patents in quantum computing keep climbing. Many of them are focused on quantum dots, about half of them I believe, and they're dominated by a few major companies like IBM and Alphabet, which is Google's parent.
What's the difference between Microsoft and Microsoft Technology?
Between Microsoft and...
The third and the
Microsoft,
last one.
Oh yes, it must be a spin-off company for patenting.
Okay.
Yeah, I hadn't... yes, you're right, the two's there. Yeah, it would be a spin-off company just for patents. Right, so this is interesting. This is out of a report that was published just last month by a London-based consultancy firm called Arthur Little. So the time when QC becomes a present risk or a zero-day threat to standard encryption is sometimes known as YQC. And the current predictions converge to about 2030. So at least two current vendor roadmaps include million-qubit commercial machines by that date. But it is somewhat misleading as most of those qubits will be required for error correction, not computing. So a million-qubit QC may have 1,000 to 5,000 computational qubits. Then we come to Shor's algorithm. Peter Shor invented his algorithm in 1994, which can compromise ECDSA, which includes EC Schnorr as well as related schemes like EDCSA. The algorithm is shown in a flowchart form where the engine highlighted in blue at the centre is the quantum computer, and the rest of the control functionality is classical. So there's no quick explanation for dummies for Shor's algorithm because it mixes together ideas from quantum physics, signal processing, number theory and computer science. But breaking RSA 2048 requires 4,000 to 5,000 clean entangled qubits with long coherence times and advanced error correction. However, this is within sights of current trends in QC development. So people might have seen this on Bitcoin Talk, where it was put out in about 2013, and it includes a quote by Bruce Schneier. So in response to the threat of QC, in August 2017, Peter Wiley wrote, "I'm not very worried about this quantum computing in general. It's got a very long way to go before it comes even close to tackling problems like solving discrete algorithms for curves of our size. A general purpose QC with several thousands of qubits would be needed, and it's not even known whether it's physically possible to build such a computer." And in 2019, Ethereum founder Vitalik Buterin is also unworried. "But for every cryptographic algorithm that quantum computers can break, we know that we have a replacement that quantum computers cannot break." So there's a little bit of complacency amongst these thought leaders in both Bitcoin and Ethereum. So we come to NIST and the emerging post-QC standards. So the US National Institute of Standards is a global leader in establishing commercial standards, and this includes encryption protocols. And for a long time, NIST has supported elliptic curve cryptography as a bedrock for internet security. But this has changed after a consultation period on the emerging risks from QC. In December 2016, post-QC schemes were called for, and various rounds of testing took place, and a late failure was a PQC scheme called Rainbow, which someone cracked on their laptop. 5.5 years later, 3 schemes are now approved for PQC usage for digital signatures. So all blockchain development teams should at least be aware of this process and its implications on easy schemes such as SEC P256K1. So here we've got a chart comparing the various schemes, and this July 2022 selection is global interest, not just in the US, so it's going to guide global PQC applications. So this table compares selected options from the 3 PQC signature schemes. All of them have much larger signatures than the current EC schemes, and usage of them will lead to faster growth of blockchain size, increased overhead and network traffic, and slower verification times, especially on resync. So SEC 256PK1 was pulled from obscurity by Satoshi and has since benefited from optimization by Peter Wiley and others, and there will also be some optimizations in PQC over time. So the Falcon authors are claiming that Falcon 512 is equivalent in security to RSA 2048. However, this is now regarded as a minimal level choice of blockchain security, and presumably Falcon 1024 gives equivalence to RSA 4028, plus the QC resistance. So a Falcon 758 version would presumably have a signature size close to 1 kilobyte. The verification times are from separate benchmarkings that have been formed by different people using 2 types of Intel CPUs, the Xeon and the Skylake, without OpenSSL or any other processing augmentation. And Sphinx is excluded from further consideration because it's just far too big signatures and it's far too slow. So looking at blockchain size impact and comparing the various signature schemes, you can see here that the Falcon 512 is a 10x increase, 1024 is 19 times, and dilithium 34 to 64. So none of them are particularly good, really, and it's really going to be a choice of what is a series of compromises made as to which one would be the best one to use in blockchains as a PQC solution.
So you get like 400 transactions in a Bitcoin block then?
Yeah, I know, it does get bad. So when Peter Wiley says, well, he can just drop in a PQC solution, it's not going to be that easy for them at all. Right, so I've done a bit of searching. Andrew Stone knows that I've had an interest in QRL. It was actually launched by Inca, who used to be on Bitcoin on the Bitcoin forum.
So who?
Inca, you might remember.
I remember it,
Yeah, so Pete Waterland. And this is probably by far the best QC resistant crypto that's out there. It uses XMSS, which is a hash-based scheme, and dilithium, which they predicted would be approved by NIST, and they were right. So that really says something about their assessment of the situation. They're moving from POW to POS, and they've got about over 10k wallets at the moment. And I went to their conference a month ago, which was in Amsterdam, and there were about 25 people. It was a hackathon, and about half of them were developers, and the other half were major investors. So it was really quite a good conference, and just shows that there is support for this particular coin. The XX network I don't know a lot about, but again it's a hash-based one-time pad system. It's account-based like Ethereum. They reckon there's 6,200 wallets at the moment according to the Explorer. Abelian is another professional one that's been set up. That uses dilithium too. It supports ring signatures. It's a power-based solution. Tidecoin is just a one-man coin where he's taken Bitcoin and implemented Falcon signatures. So there may be something useful to obtain out of that for lessons, but it's not going anywhere. And Can platform is really just two tokens, an ERC20 and a Binance chain BEP20, and they've got their own network which provides a dilithium wrapper on these two tokens, and there was a bridge between them, and last week the bridge got compromised and all the QANX taken, and the price of this has collapsed to zero.
Strange.
And Crown Sovereign is a bizarre one. It's the only one, well, QRL's got a price, it's number 800 in the rankings. The price is 15 cents. Crown Sovereign's got a 50-cent price, but there's no known users, and it's closed source, based in Newport, California. So I just don't know what's happening with that.
Are these are there any like advanced features with these signatures? You know, like multi-sig, anything like
I
that?
believe
Aggregation.
QRL has got multi-sig. Aggregation, I think, is a bit of a problem. Now, QRL's partnering with a team called Geometry Labs, which is just a group of mathematicians and computer scientists who rent out their services, and they have come up with aggregation schemes which are enabling QRL to go to a POS protocol. Because, of course, with proof of stake, you've got this network overhead of everyone proving what their stake is.
So that would be over dilithium then?
Yes, I guess it is over dilithium, and that's something we'd need to have a look at. But there's probably a few useful things, and the ring sigs that Abelian have produced would be worth having a look at as well. Just go on to the proposal for Nexa. So this is just a high-level list, and whether it happens or not is up to the people in this room. But I suppose I suggest supporting a PQC6 scheme in parallel with what we're doing at the moment, which is Schnorr. And then at a certain time we would default the wallet software to use the PQC addresses, and then at time 3 we enforce all new addresses to be PQC, but obviously support the moving of balances. Now this is where time is not the friend of blockchains, because the more time that goes on, the more people get wallets, the more address reuse occurs, the more public key exposure there is, and the actual inertia to moving to a PQC system just keeps growing.
So the problem is that a hash could be quantum resistant, but as soon as you reuse
Yes.
an address,
Well, that's the same. That's the case with Bitcoin at the moment. What Bitcoin's very safe, provided you never use an address. If you do use it, if you do move it, then all of a sudden you've opened up a QC window. And
So you're saying the double SHA-256 is quantum
Yeah.
resistant?
yes, it is.
Okay.
So
So then
So
it
you
next
sit-
that our default addresses will have that same
yeah, they will.
situation.
They
will
will.
be quantum
But
resistant until you
until
spend.
until you spend it, or until you reuse the address.
If you use your address for another that.
Yeah, and the problem is users are going to keep doing that.
That'd be like,
So anyway, something for everyone to think about, because I think it is an emerging threat to blockchains, and there's a lot of complacency.
yeah.
That's it. Thank you.
Thanks very much.